Everyone. My name is Sherry Praske. I'm with the Solid Waste Association of North America here and also on Joanne's board. So I'm on the Saskatchewan Waste Reduction Board. And yeah, I just wanted to welcome you all. I really want to thank CPIA for the sponsorship of this session. And I think we're just going to jump right into introducing our first speaker. But as Joanne had said, feel free to come in with a chat if there's questions during the speaker. I will be watching that. There is also the opportunity to do it visually after, but we'll start with Louis. Louis is the co-founder of Sweet Gazoil and the co-inventor on many of the company's patents. He has over 30 years of experience in finance, accounting, administration, and business development. He has worked in a range of business environments, from director of planning and analysis for a division of one of the largest banks in Canada to vice president of finance and administration for privately held corporations. So welcome, Louis, and we will got your presentation up.
Well, I'd like to go through the agenda. First of all, if we're going to talk about plastics and plastics recycling, the first thing we should know is a little bit about plastics. Then we'll go into the end of life for plastics, which is sorting and processing, because the two are interrelated. Let's just go. Everybody's plastics is one type of, something similar from one place to another. As you know, there are 7 types of plastics as far as recycling is concerned. And just in a bottle of plastics, how many types of plastics is there in a bottle? And because I can't really ask question on this one, I'll make it easy. This bottle looks fairly homogeneous. Actually, it's got 3 types of two to three types of plastics in there. First, you've got the PET, which is the main crystalline bottle. Then you have the LDPE for the labels, and sometimes it's paper. And then for the caps, I've seen caps in HDPE #2, and I've seen caps in polypropylene. So even a simple bottle, and a bottle, how much does it weigh? It weighs about 10, 11 grams. So you get a lot of different products in a very simple bottle. Now, if we go even simpler into a plastic bag, how much does it weigh? Because the value you're going to get is going to be changed by the amount of weight you have. What's the bag's material? What's the virgin resin price? And once you have sorted it, so if you look at it, the bag's weight is 5 grams, which is 0.011 pound, or it's made of low density polyethylene. If you look at the virgin resin price, it's about 50 cents a pound, which makes it for that item, it's a couple of at 5 grams, it's a couple of pennies, not even. And at the sorted price, it's not even 0.02. It's 0.02 cents. So so you have to go through a lot of volume to get something valuable out of it, and that's the key problem with plastics. So light. When sorting sessions have been making most of their money with fiber. Most of the recycling started with fiber, with newspaper, etc., which are going down. Actually, the amount of paper that was done in the U.S., there was 67 million tons, and the space that they would, because of the density, we calculate about 447 million cubic meters. Now, all the recycling has been made mainly because fiber was producing most of the revenue. The problem now is that fiber is going down by 10% or 15%, depending on the years, whereas plastics is going up. Well, plastics is a different material, much lighter, and takes a lot more volume. As you can see, just in a given year, in the recent years, the plastics weight was 20% as far as as far as the waste stream was concerned, but it takes 35 million tons. So it completely changes the way we can sort it. Somebody who can make a profit out of fiber, even if the plastics had more value, the way of treating it is much different because the volume becomes a key component for the sorting part. Now, the bulk density we were talking about, more, you can transport 10 times more. You can see the difference between, we have to think not only in weight, but also in volume, because plastics is bringing a total different way of doing things. In other words, if I garbage truck 3 liters and took, food, then I could fill it out completely with food and I would be overweight. But only 0.9 tons of plastics makes it a totally unproductive load. So it's not all bad compared to fiber, but we have to take it differently because plastics have different characteristics, can't be used exactly, we can't use this exactly the same systems as we were using for fiber. And that's why there's such a outcry right now with plastics. People are not used to it, and we're not adapted yet to it. If we look at the plastics production, there are 7 types of plastics, which other being 5%, but some plastics are, I'll call them polyolefins, HDPE, LDPE, PP, and PS, have one characteristics. They're made up only of carbon and hydrogen. They have no other atoms. So they can be treated in many cases. If you go down to the atoms, it's very simple. There's no complication because it's only carbon and hydrogen. Looks simple, but if you look at all the various geometries, let's look at the properties and structures. As you can see, has some O's in it, which is because it's usually made out of 2. The density of 100 kilograms per cubic meters. And see that PET and PVC have higher densities than the rest of the plastics, which is HDPE, LDPE, and the rest we don't take into consideration because they're a small part of it. But it's important to notice that the polyolefins, which are the HDPE, LDPE, PP, and PS, are much lighter than the PET and the PVC, so they can be separated by density. Now, if you look at the composition of polyethylenes or polymers, that's what we call plastics. Usually, they're polymers. In other words, what they are is they're a simple molecule like a monomer, and let's here take ethylene, and they are being joined so that they form very long chains. And actually, a polyethylene molecule might be 50,000 carbons. So a chain of ethylene, many ethylenes up to 25,000 to and over of links made together to make one very, very long molecules. And that molecule is exactly the same as fuels. In other words, petroleum diesel has exactly the same structure if you look at it on the chain side, and the only difference is the amount of carbons in there. In other words, diesel has 16 carbons, whereas polyethylene will have 25,000, as I said before. And if you go down to gasoline, you're at 8 hydrocarbons. That's why we often call it octane. But it's very surprising to see that plastics are actually, or can be shown as being very, very long chain of fuels if you put it. End-of-life plastics. There are many ways of end-of-life: landfill, energetic recovery, generation of fused-derived fuels, which is popular in Europe especially. Then you have sorting and selling, which is seen as better. And then once it's been sorted and sold, often to get the real value of the plastics, there's processing. And we've divided the processing because right now there's a lot of interest in processing the plastics to make something valuable out of it, because sorting and selling is not providing quite the value that it should. And we've reviewed 81 technologies, and we've and taking a study from Closed Loop Partners, it's divided into purification, decomposition, conversion, and we'll go into more details into this. A couple of rules of thumb when you're processing and looking at plastics, and it comes from the petrochemical industry, is value is driven by purity and size of molecules. In other words, if you look at number 2, plastics need to be 99% pure to be useful in manufacturing. And that's key. Actually, China never stopped importing plastic. All they said is, your plastic that we're going to import has got to be 99.5% pure, which is impossible just by mechanical sorting. And this is compounded by the fact that often, polyethylene or polypropylene or polystyrene have got additives, and on average, plastics have additives, coloring and changes in property like melting point, etc., which is about 6% of the plastic. So getting 99% pure out of plastic, out of 7 categories of plastics, and on top of that, I've got additives, is mission quite impossible. And the last thing to remember, because plastics are so volume intensive and so light and have such low density when they're being recycled, is you have to look at quantity versus quality. A lot of the recycled plastics that people say we have recycled plastics is actually coming from the industrial side, which is, little pieces that have fallen off the production line. Whereas post-consumer plastics, there's a lot of it, but the quality that we're able to get from sorting is very low. Just to give you an idea, we've put price versus over the years versus diesel being in black. You can see that even sorted and clean, the value of plastics is way below the diesel, and especially mixed plastics. If you look at the blue line at the bottom, which is commingled 3 to 7, or even the yellow line, which is commingled 1 to 7, because they're mixed plastics, they have practically no value and very difficult to sell. So not really worth the sorting of it. But if we can process it, maybe we can, on the sorting side, and we'll go more into the details of sorting. People talk about sorting, but often there are 6 main ways of sorting. There's 6 sorting principles. 1, appearance. 2, optical sorting, density. And 3 that are less known, which is triboelectric properties, terminal velocity. First of all, everybody by now in a sorting center will know hand sorting on a conveyor belt. I told you, material sorted will be PET bottles or HDPE bottles and jugs, or how to call it, bags, etc. But the problem is, by the time the person has selected a bag or a bottle, the price that I'm going to get out of it more than what I've put in to try and sort it. And there's the optical sorting, which has become very much more popular. Is the detection with optical sorters, which is air jets at the end of a conveyor or even by robots. Example of the material sorted is colors and shape, and type, or X-ray. The problem with that is it's broken down in many pieces, and to get good value compared to the price of the machinery. It might be good in the future, as I think the price is going to come down for these type of robot assist. Starting by density, which is a sink float system or hydrocyclone or atypical. This is where PET and PVC can be sorted from the polyolefins. Okay, very good. So if I sort by density, it's going to separate mostly the heavier plastics, as we said before, PET and PVC, from the lighter plastics, which are HDPE, LDPE, PP, PS. The big advantage of that is that the processes afterwards can take mixed plastics often, or the PET and PVC can be separated later. So, and it's easier to do than manually. And triboelectric. Triboelectric properties that we don't see it very often. What it's done for, it's you take friction, you take static electricity with positively charged electrodes, and the materials getting sorted mostly are PVC versus PET. You got to remember that PET and PVC are very incompatible. So if I get 1,000 or even 10,000 PET bottles with one bottle of PVC, just as an example, the whole 10,000 batch of PET is going to be no good. It can be no good. So it's very important that the two are separate. So this is why you would use the triboelectric, because they have this density. Another way of sorting by density is zigzag separators, which needs a relatively consistent particle size, and the airflow causes some material to float, the lighter ones, which is probably the HDP, the bags and the LDPE and the films, and it will sort the rigid plastics from the plastics films. So it is a possibility to, it's a bit like density sorting, and it gives you fairly good results as far as sorting the polyolefins versus the PET bottles, or even rigid plastics like HDPE, which might have a higher value. Finally, ones I haven't seen that often is the flotation, and depending on what's in the bath, bubbles are blowing up and will pick up certain types of plastics, whereas other plastics will be at the bottom, and then at the top you have paddles that take out the plastic that has floated up. Examples is polystyrene versus PET PVC, and PET from PVC. So or polycarbonate. So it's used, but I haven't seen many using it. So this gives you the general feel for the possibilities of sorting. Let's now go into processing of various plastics. You remember I told you there was seen, at least from closed loop partners, from a report from closed loop partners, 81 different ways of processing plastics. And we'll go from purification, which is just cleaning up the material, to decompositions into monomer, conversions into fuels, or generally into fuels. Purification, which is, in other words, these plastics is sorted and then melted and put back into plastic pellets. The problem with that is the additives and degradation in the extrusion. So you need additives. So you can't redo, apart from PET, which is pretty good, it makes poor value items, which is downcycling. Things like bottle into carpeting. As you can see, PET is at the bottom. See the number of technology providers.
Louis?
Okay, the number of technology providers is at the bottom. You can see that that type of cleaning is used mostly for PET. There's some trials being done with HDPE, LDPE, with the polyolefins, and one for PVC, and some of the others are there. There's some have the dissolution, which is sorting and purification, and you dissolve it in one of the. I'm often here in Quebec. We have polystyrene, which does a solution of polystyrenes. Then you filter it, you precipitate it, and plastic pellets. The advantage of that, as you can see, it's good for PET and polystyrene. So you have downcycling, which is fairly simple because you can't really do the separation of all the additives and the various types of plastics. What you do is you do general sorting, cleaning, and then you melt and do regranulation, except the plastics you're going to get is not very good for making bags or films that are very consistent. So usually what they'll do is plastic lumber or solid fuels. There's less sorting, but low value products. You have decomposition, which is solvolysis. After the sorting and purification, you put it into a solvent. I think everybody knows what a solvent is, so that you get a monomer, and then from the monomer, you repolymerize to get plastic polymers. It's very popular with PET. We have a couple of Canadian companies in there, and there's some tryouts for the polyolefins and some in the others. Same as solvent, but on a biological, so an enzyme basis. So you have sorting, positioned by an enzyme, and same. Once you have the plastic monomer, you polymerize, get back to your original plastic. It's a good plastic, but it's fairly expensive. As you can see here, there's 8 processes for PET, so it's PET is probably the only this seems to work well. There's pyrolysis. What you do is you decompose the plastics into by thermal decomposition. You bring it up to about 500 degrees, 130 degrees Fahrenheit, and the pyrolysis of PVC and PET is not recommended because you'll get hydrochloric acid or naphthenic acid. As you can see, it's very good for, you've got 27 technologies, and if you include the other 27 plus 3, but 27 technologies, mostly in the polyolefins. As you can see, excluded are the PVC and PET. And they're usually produce fuels sometimes, or you can produce naphtha to bring it back to plastics once you send it back to the plastic manufacturer. Then you have hydrothermal liquefaction. There's only one company that does it. What you do is you take your mixed plastics, put high pressure and temperature, and supercritical water. So you have high pressure, 218 atmospheres, which is quite a bit, and 374 degrees. So it's really pushing. It's really difficult to attain. But there's one company who's specializing in pushing the technology. Then you have gasification, which I think everybody knows. It will be very high temperature, so often it'll be both biomass and plastic, but plastics will give you probably the highest conversion rate and the less energy needed to do this conversion. And that about gives you an overview of all the various ways of treating plastics. Sorry for the sound, but happy to provide any answers to questions you might have.
Welcome, Pierre. Now, thank you, Louis. Yes, we will have some more discussion after once that comes back into your mind as well. But Pierre is a senior consultant in recyclability and market development. He holds an undergraduate degree in biology and a graduate degree in environmental management, and has held several functions over the past decade as a special advisor for various private and public organizations, focusing on enhancing their recovery and recycling programs or processes. So you're joining us from Montreal, is that correct, Pierre?
It is, and I hope the connection is good.
Yes.
So, feel free to tell me anytime if connection is not good, and I try to see what I can arrange.
Awesome. Sounds good so far. Thank you.
Well, hello everyone, and thank you, Sherry. Thank you for the Saskatchewan Waste Reduction Council to give me this opportunity to talk to you about plastic recycling. I have to say, I became a Canadian citizen last year, and I promised myself to visit every Canadian provinces. Saskatchewan was on my list, but at that moment, I think it looks like very much to Montreal. I'm kidding, obviously, but I hope I have another occasion to visit your province. So, before we go, and you will see that my presentation have a similar topics of the one from Louis. But before we go in the future for plastic recycling, I would like to have first to have a look at the current plastic recycling situation. So we all understand that plastic recycling has gotten more and more traction in the last years. If you don't know that, maybe you were living in a cave or you took the lockdowns too much seriously. But plastic recycling, even if it's got traction, have challenges from price pressure from the oil and shale gas industry. It has challenges regarding to low demand for certain material, such as plastic films or PVC. I know there is no buyer for PVC from packaging in North America at the very moment. And also you have some technical or sometimes economical recycling challenges for certain material, such as PET trays or polystyrene, let's say. PET tray is a good example, actually, because one of the solutions to recycle PET trays is to use the same process and to mix it with PET bottles, but in a very limited proportion, around 15% usually. So as you have more and more PET trays on the market at the moment, the quantity that is recovered exceeds somehow the amount of integration you could use. So then you need to find new end market for that kind of packaging. And that's just an example, actually. But even so, there is challenges. We can say that in Canada, we have a fairly good post-consumer recycling capacity, especially for certain resins such as the polyolefin and the PET, and especially on the most populated provinces such as Ontario, BC, and Quebec. But as you can see, there is some material that are not so recovered and recycled, such as the LDPE films that you will find in yellow, or the PS that you will find in black. And really, the question is, because as we can pretty much sort every type of plastics, as Louis showed the various technology, there is a lot of different possibility to sort the plastics at the moment. But the big question is there a market for the material that you will be sorting? And is the value from that sorted material will at least cover the cost of separated, clean, and convert the plastic into a plastic, recycled plastic. Just before, I wanted to go back to the previous slide, which were the plastic recycling capacity in Canada. So this is where you can see that we have a good capacity for mainly PET and polyolefin, and less capacity for other resins such as LDPE and polystyrene. Then going back to that slide, where I was talking to you about the having the capacity to sort, clean, and convert plastic in an economical way. This is one of the biggest challenge in the plastic recycling industry, especially for post-consumer. And it varies from in many different ways. It varies from one province to another. I know in Quebec, the plastic recycling rate of packaging collected curbside is around 18%. I don't know the one in Saskatchewan, but Joanne told me that it was not that good. So compared to Quebec, at least we don't know, but we know Quebec at 18% is not a good, high recycling rate. There is also differences between the resins. I mentioned that there is no buyer for PVC in North America, so the recycling rate of PVC in Quebec is 0% at the moment, and around 0%, and the one for PET is closer to 45%, actually. And then you have also differences in type of packaging. You have bottle recycling bottles are well recycled compared to laminated plastics such as the toothpaste. So why is plastic recycling so hard to raise? Before we go in the details of the technology, I'd like to go back to the production chain, and Louis talked to you about that earlier. But so the plastic production chain is very important to understand to clearly understand the basics of mechanical and chemical recycling after that. So at first you have hydrocarbons that is transformed into raw materials, and then in monomers. The monomers are binding together to form polymers, and then the manufacturers use different additives, as Louis told you, and those additives make products such as packaging. And those packaging eventually will become post-consumer plastic that will be put into recycling bin. The phase where you link a monomer to form a polymer is called the polymerization. And if you allow me, I have a 5-year-old son, so I use a lot of analogy from his universe. So let's see a monomer as a building block of Lego blocks. And when you clip together those different monomers, so those different Lego blocks, you have a polymer. And you will understand why I use that analogy in the rest of the presentation. So at the very moment, how is the current recycling working? Well, you have recovery and mainly mechanical recycling, and this is at the very end of the plastic production chain. So with recovered plastics, you are making new products. This is how it works. And specifically, so you have the collection and sorting, which is the recovery. The mechanical recycling works by mainly grinding, washing, and extrude the plastic to make different pellets. But there is limits in actual mechanical recycling methods. The first limit is the resin quality. So the presence of the additives, the glues, the coloring, and all the mineral charges diminish the quality of recycled resin. And the different colors as well. So if you do not separate the colors from different packaging, you will end up with the gray-green pellets. It's pretty much the same thing as if you make a soup or if you do painting. If you make a soup with tomatoes, with zucchinis, and let's say, I don't know, potatoes, you mix it together and you will end up with this greenish color. Same thing with the paints, and same thing with the plastics. So the importance of the separation of the different plastics by resin, by mechanical properties, and even sometimes by colors, make plastic recycling relatively costly, actually. And, you know, it can be competitive to the actual virgin plastic production. If you look at transportation, we transport the recovered plastics and the recycled plastic at the end by trucks, which is maybe one of the most costly way to transport stuff. On the other side, the virgin plastic is transported mainly, the feedstock at least, is transported by pipelines, which is very economic. And if you compare the production as well, so you have the smallest virgin plastic production capacity may have a bigger production than the biggest recycling operators, such as Merlin Plastic that you have in Saskatchewan. So costs are relatively high, but you have also an impact on mechanical properties within every recycling cycle. At every cycle, plastics lose part of their mechanical and aesthetic properties, and then it limits the percentage of potential recycled content you can put in new packaging. And speaking of which, there is already gaps between the different recycled content commitments and the material that is available on the market. First gap is between what is generated and what is getting recycled. As you can see on the slide, this is data from Deloitte that have done a study for Environment Canada. So you can see a huge difference from what the quantity that has been put on the market and what is actually recycled. And even from what is recycled, what goes into new packaging application with recycled content is even limited. And I know that the Recycling Partnership has done a study on that regarding PET, and they found that around more than 1,000 million pounds of PET was missing in the US only. So that gives you the picture of the global situation. So we do understand that there is a need for new recycling routes along with the current mechanical recycling. There is a need to bridge the gaps with recycling targets. There is a need to meet the quality requirement from the manufacturers. And above all, there is a need to reach those quality requirements from North American manufacturers, actually. However, these new recycling routes have to be developed with the help and the collaboration of the actual and current mechanical recycling operators, because this is not two realities to oppose, mechanical and chemical recycling. And to explain why, it's because most of those new technology allow us to think that we could recycle the plastic not into product directly, but into the original form of the plastic, which are raw material, monomers, and polymers, as Louis told you. But there is a need for, let's say, a feedstock preparation, and this is where there is a collaboration needed with the actual mechanical recycling. Those new technology could not take the plastic bottle as is, or this plastic product as is. There is a need to convert and to transform that product before we go to those technology. To say that differently, let's say that if within the actual mechanical recycling technologies, you can go to 90 to 95% purity level of the pellets, going to this, taking this 5% left to reach the virgin-like quality could be done by the chemical recycling process. But the chemical recycling process itself could not go from 0 to 100%. So in other words, we need to find the sweet spot of the collaboration, and I think it's important to mention at that time. That said, Louis told you about the new recycling technology. There is three categories. Purification is one of them, and this is why I use the Lego analogy. So if I try to just explain that with a Lego analogy, so you have this polymer with the additives that are represented with these green and purple blocks. The purification allows to go back to virgin-like polymers by getting rid of those additives. The decomposition then can allow us to go back to monomers or sometimes to polymers by getting rid of the additives, and also by breaking the molecular bonds between the different monomers. So you go back to the monomer phase of the production. And the last one, the conversion, producing mainly fuel and petrochemicals. They are also breaking the bonds, but they are not making that as selectively as the decomposition, as you have heard earlier in the previous presentation. Louis presented various technology providers, 80. I have a count of 60, but it depends on what stage of maturity you consider. But the conclusion are pretty much the same, from 60 to 80 technologies. Most of them are in conversion recycling technologies, and most of them are using polyolefin and polystyrene as feedstock. And fuel and petrochemical are the major end markets of those technologies. So you are not necessarily producing a new packaging with those kind of technologies. On the decomposition part, which is the other big technology type, about 2/3 of the decomposition aim PET and polyesters, such as textile. And about the maturity, we can see that most of the most advanced technology are in the conversion. The other one are either in early commercial, but closer to a pilot or a lab phase, actually. But few of them are very proven at an industrial stage yet, apart from the conversion technologies. That said, what are the anticipated benefits from chemical recycling? I identified 3 of them, and it is a way to overcome the challenges I presented to you earlier. So first, it allows for separation of the different additives, dyes, mineral charges, and then you ending up with a potential virgin-like quality, and it's represented in the picture on the slide. Pure Cycle Technologies, which is a technology provider, illustrate that point with polypropylene pellets, actual pellets, and what it aimed to get a more translucid polypropylene pellet. So that's the first one. The second one is there is potential no loss of mechanical properties of the plastics. That means technically and theoretically, an infinite closed-loop recycling for plastic is possible, as for the glass or the aluminum, for instance. And the third one is it allows recycling of hard-to-recycle and non-packaging plastics. Maybe textile is one of the best examples. So that's for the pros. But are we there yet? There is challenges to overcome to get to that point. And for technology providers and for the actual recyclers using that technologies, there is a need to secure sourcing and sell. But most important, there is a need to scale up those technologies to an industrial stage and assess the process environmental impact. Because if you remove things such as additive, they are not disappearing. So you have to deal with that residue sort of. And that residue could be potentially harmful if you think about brome flame retardant in the polystyrene used in the construction industry, for instance. So we need to assess that in the next future. And we, as an industry, as a recycling industry, we need also to help those developments by adapting regulation and by pursuing the recycling targets that brand owners and governments are making, and eventually invest in technologies at pilot and early commercial stages. And obviously, as I mentioned, work with the current recycling operators, since they are a big part of the process. So that gives you a brief overview, that complement what Louis said. I'd like to end with 3 general ideas of the presentation. The first is markets exist for recovered plastics. If we make something out of plastic, then it becomes a market for the plastic we are recovering, and we should find a way to reach those manufacturers' requirements. The second conclusion, the second idea is that technology providers and the actual users will need to work with the actual operators. As I mentioned, there is a collaboration needed, and there is not 2 different realities. And the last one is, it's not possible to be competitive with the virgin plastic production. So the biggest question is, what is the economic model that will allow the recycling of all the resins? Yeah, that's pretty much the biggest question we have to find out. Thank you very much for listening, and yes, I'll stay there for the different questions.
Thank you, Pierre.
Hmm?
I just see a big question just came in. I'm just looking this up. Okay, I'm just going to read this one out. To simplify all this, rather than pursuing more and more complicated processing methods, is it time for governments to force legislation for fewer formulations, outlaw black plastics, outlaw colored styrofoam food containers, trays? We need to simplify, not complicate. That needs to be part of the new economic model. It's a statement, and it's common sense, but I'm pretty sure that's exactly what you guys just said.
Yeah. Well, by my opinion, I think it's both, actually, because even if you simplify and let's say you have one type of industry that choose to use one type of packaging on what type of resin. Let's take the example of bottle, which is maybe one of the best example. In the beverage industry, a lot of the manufacturers use PET, and that's why PET bottles are more easily recycled into new bottle than I don't know, PP or polyethylene. But at the end, even if you simplify that and you make everyone agree with the potential type of packaging for one type of industry, you still have some limits. As I mentioned, you still have limits of, you cannot recycle indefinitely your products, and then the recycled content you are making could not be reached within the current methodology. So it's kind of both, actually. Those technology will help part of that. But obviously, if you simplify the production at the beginning and you remove part of the additive that are detrimental to recycling, then you are helping for sure.
The only part that's got to be careful on this is that a lot of the additives provide huge productivity improvements to the packaging, etc., which is a small part of the total cost. So yes, you might be better for the recycling, but the front end cost you have to balance it against the front end cost to make them, and the amount of energy that's needed to make the material. So at this point, I'd say yes, it'd be good if the government would tax more, and I think that's happening a bit in Quebec. The material, the plastics, to help with the recycling. But until the technology, I would give it another 5 years so that the technologies can mature to a level that makes it easier to take a good decision and not block some technologies by overly regulating the front part or the recycling. So it's a double-edged sword. It's good, but it can be dangerous.
And the time to do it could have been many, many years ago. We'd be in a much different situation, but it sounds like if that's what's happening in Quebec, it's a coincidence that both of you gentlemen are presenting from Quebec. So anyways, okay, thanks, Merv. Another question, the energy involved, are you guys able to comment on the energy involved in some of the new recycling methods?
Yeah, you have to look at the total cost of the energy, as Pierre was saying, which was very valid. Is a lot of the petrochemicals save a lot of energy by building huge plants, but then you have to balance that against the trucking and the collecting of plastics, which is very light and does not transport well. So the amount of energy that you're going to use should take into account the transport and the sorting energy that you need to get to a product that is valuable. So, but the energy, let's say in pyrolysis, which I know best, is about 10% of the energy that is needed to make a fuel out of it. You don't get the same, you don't get the plastic, but at least you recover, I'd say, about 50% of the value of the original resin, rather than throwing it all away. So there is the amount, and the energy actually comes from the plastic itself. So depending on the technology, most of the energy will come from the plastic itself and will be much less than the recovered item.
If I were to complement, I know that, well, I can give you a link of the study that Louis and I were mentioning, which is a study from Closed Loop Partners, and you will have the data sheet from every technology provider so that you can find information from them. But if you take some example for the decomposition, for instance, of PET and polyesters, it's something that has been used for at least a few decades. Japanese has planned in the 80s and 90s on decomposition of PET, actually. But the impact they had is it was a higher demand on energy. What these new recycling technology and the new technology providers came with is technology that have a lower demand on energy than the previous version that the Japanese used to have. I know that one of them is, for instance, Loop Industries. I don't want to do any name dropping, but that's one I know better. So Loop Industries is doing his process at an ambient temperature. So he's not requesting to have a higher temperature than other type of decomposition. So to that point, the energy demand will be lower. And he has a life cycle analysis to compare his product to recycled product made with mechanical recycling, and with PET that ends up in the landfill. So very depends on different technology providers.
Yeah, it definitely sounds like there's a lot of different ways to calculate, and a lot you can go back through the supply chain. So definitely. Okay, thank you. Two last questions. One is there a byproduct of chemical recycling? Or what are the byproducts when you break down plastics chemically?
It depends how far you go. If you go pyrolysis, which is a breakdown, quite a bit of a breakdown, you don't get any. You get plastic char, which can be used in a cement kiln. You get fuels, and the rest is used to drive the process. So there's no real byproducts if done well and accurately. Right now, it's still a bit in its infancy, so the projects are not totally good. If you look at somebody like Parawave, which wants to decompose styrene, well then it is possible to decompose styrene into monomers, but then you get benzene and toluene, which I think they can sell once they have separated the monomers from the other components.
Okay, so you're seeing that there seems to be markets for what's left over when kind of that would be with the end game in sight, I guess, which is our
most of it.
Okay. Pierre, anything to add to that?
Oh, I think that's covered well. Yeah.
Okay. And I think finally, is there any system that chemically recycle PVC?
Not that I am aware of. However, there are people who will take, PVC from windows, and a lot of the PVC because there's little PVC in post-consumer, but there's quite a bit in the construction industry. And I know a couple of companies that specialize in taking that PVC and then remolding, like how to call it, window frames, PVC, and they will take that PVC and recycle it. So there is some recycling in the construction industry. In the packaging industry, PVC is now being banned in most cases, voluntarily. I mean, if you look at the Chemical Alliance or Council, then the Chemical Recycling Alliance, most of them are banning PVC labels, and so there's very little PVC now being put into consumer packaging as much as possible.
Okay, and thank you, Pierre, for the link. It's in the chat if anyone's looking for that.
Mm-hmm. And I'm not aware of any chemical recycling of PVC as well, so I don't think that's one of the main resin that is focused on.
Okay. Well, thank you all. Yeah, I really appreciate it, and I'm hearing lots of thanks on the chat. Thanks to the guys from Quebec. So thank you, and yeah, really appreciate it.
Thank you.
Look forward to getting you into Saskatchewan sometime.
Yeah, hopefully.